Okay, our electric circuits are still here, and this is our lesson 3 on these electric circuits. So we're going to deal with electric circuits where internal resistance of the battery is negligible. So in this situation, we want the battery, as you will see, we won't have any little r, meaning the internal resistance. It will be negligible in these examples that we're going to do. And then in the next video, then we can introduce the ones that have internal resistance. So let's quickly figure out how these circuits work. And as we can see, we have a 30-volt battery. So that's the voltage across the terminals of the battery when it's in use, even when it's not in use. So that is what we have. We have our resistors. We have 16 ohm resistor here. We have a 48 ohm resistor. The 3 ohm resistor is also over here. From what I said, you should know how current flows. So this is the positive terminal and that's the negative terminal. Current flows like that. That's conventional direction of the flow of current. So it's total current that comes out of the battery. What it means is that A2 will record the total current, and then still that total current will flow through there. Then come to this point, there will be no current that go through the voltmeter because of its very high resistance. So all the total current will pass through the 3 ohm. And then when it gets here, it branches. It branches at a ratio that is opposite to the ratio of the resistors. So since the resistors are at a ratio of 1, 16 and 48 is 1:3, right? It means when current branches, it will branch at a ratio of 3:1. So that is how it branches at that point. So most of it will go this way, and some of it will come this way, and then again it combines at that point. And then as you can see here, the total current will flow through A1 and right through the battery. So you have to really understand your circuit, please people, before you try to answer anything. Well, now that you have that, let's go and figure out what to do with the first question. So we have to determine the total resistance of the circuit. So to do that, we have to know where our resistors are. So you still remember them, right? So these ones here are in parallel with each other, the 16 ohm and the 14 ohm. 48 ohm, so then this one will be in series with these parallel ones. So we first of all have to find the resistance for the parallel combination. I usually would just go and say product over sum. So for me, this is just for me, product of the two over sum, which is 16 plus 48. I should be able to get my resistance with no problems at all as 12 here. 12 ohm. But on the other hand, you, however, are supposed to solve it like this if you do caps. So you actually have to write that formula down and then substitute it in, wasting as much time as you can. So here, your first resistor is 16 ohm, right? Plus 1/48. So this, I believe it should be 1/12 when you simplify it. And then to get your resistance, you're just going to invert that one. So let's invert that part and see what will happen. So that will be 12/1. It will be 12 ohm. Okay. We didn't want to calculate the resistance of the parallel combination. We wanted the total resistance. So to get the total resistance, we will have to also include this 3 ohm resistor over here, this one. So I'm going to have to say total resistance is 3 ohm plus the 12 ohm. Well, I think it's clear to everyone that the total resistance will be 15 ohms over there. So that is what we were hoping to have, and that is precisely what we have. So here we are. So let's see if we can get the readings on both ammeters, that is A1 and A2, quickly. So let's find out what A1 is. As you can see, A1, where A1 is and where A2 is, they are both recording the total current flowing in this circuit. It's only this one that is recording the current flowing in the 16 ohm. So A2, which is this one, and also A1, this one, they record the total current in this circuit. So let's go and calculate the total current of this circuit. Maybe to be able to do that, let me carry on doing it here. So I'm going to answer number 2 here. From what we know, V is equal to IR, isn't it? So if I want to find total current, I will have to use the total voltage and the total resistance. To emphasize that, I'm going to just put a little t on these ones to say total on all of them. Well, if I want the total current flowing in this circuit, I'll have to use the total voltage, which we were given to be 30. So I'm going to write 30 over there, and then over the resistance, the total resistance that we just finished calculating here. Okay? So you remember it was 15 here. So we're going to say over 15. As you can see, our total current is going to be 2 amps. So there are 2 amps flowing in this circuit. So we would like to use that as much as we can in the next questions. Let's see what that is. We're still on question 1, right? So we're still using the very same circuit. We would like to find now the reading on V2. Look at where V2 is, right here. Okay. Is the voltage across the 3-ohm resistor. So if I want to calculate voltage, from what I already know, voltage is current times the resistance. So, do you know that we know the current flowing in the 3-ohm resistor? Remember, it's the total current flowing. It hasn't branched yet when it passes 3-ohm. So, we would like to use the total current, which we said was 2. And then our resistance in question, we want the potential difference across the 3-ohm resistor. So, as we can see, V2, this is all V2, will be equal to 6 volts. Just like that. So we know that at this point it's 6 volts. From what we learned back then, I'm going to use that to explain this one as well. From what we learned, we said that if we have appliances in series, the total voltage, you can get it by adding the respective voltages available. So in this situation, we seem to have 2 things in series. What are they? That is this part here, this voltmeter, across the 3-ohm, and even if I were to put a voltmeter reading here, across the parallel combination. So remember, even if I were to put a voltmeter reading over here, it will be the same, my pen, or is it me? One of us. All right, so if I had that, let me call it V parallel. To get the total voltage, I could easily add V2 and that V parallel. I should be able to get 30 volts. But from what we said, that V parallel that I just finished putting should be equal to V4, because it is in parallel with it, and it should also be equal to V3 because these ones are in parallel with each other. So that leaves us with just one thing. To get the V4 or V3, we just have to say V2, or let me just say V total in this situation, is equal to V2 plus any one that you want of the 3 that are here. So these 3 are in parallel. You take one of them. So since they are all in parallel, let me just take V3. Let me take V4. That's all you need to do. You don't take all 3 of them, V3, V4, and that V parallel part. No. You just take it once and you're done. So the 30 volts, that is the total voltage, should be equal to V2, which we said was 6. So the difference between those will be the reading on V4. From what we are gathering, this should just be 24 volts. Okay? So V4 is 24 volts. So it means V3 as well should be equal to 24 volts. You can see that they are in parallel to each other at that point. Well, I was going to work it out differently. We can actually work it out differently. Let's do that. Let me bring it closer to me now. Right. So I want you to see this. I said to you, I'm going to erase everything. Right? I said the resistors are at a ratio of 1:3. So current, when it comes, it will be in a ratio of 3:1. So I could have calculated the current flowing in that direction. How was I going to do so? I was going to use the 2 amp that's coming, and I was going to say, to calculate the current in A3, say for example, I was going to say 3 of, because we have 3 parts here, these 3 parts and then this 1 part. So it means it's 4 parts. We are going to divide 2 amp into 4 parts. It means each part is 0.5. So to get the one that goes in this direction, I have to say 3/4 of 2. That is how I was going to get 1.5, isn't it? So I could have calculated 1.5 here, amp, the current, using ratio, and of course, using Kirchhoff's laws, I was going to get the current flowing in this direction as just 0.5, 1/4 of 2. After I do that, after I calculate my current like that, I could easily calculate this V3, because I was going to say V3 is equal to the current coming, which is 1.5, multiplied by 16. As you can see, I was still going to get my 24 volts. And I was going to do the same for V4 as well, if I didn't have a faster way. So at this point, I'm saying you could have said 0.5 times 48. Either ways, you are going to get 24 volts. So please, people, this is yet another method you can use to calculate this. But I would like you to stick to the fact that if you add the voltmeter readings, which is this one, V2, and the voltage across this whole part here, which we can see as V4 or whatever, if you add these two, this one and that one, you should be able to get to the total voltage. I hope you can still see this circuit. Right, so let's use that one quickly. Let's carry on. So what was I saying? We got our 24 volts. Let's go and finish off this sum. Well, it does look like we are in need of space, a whole lot of it. So let's create a whole lot of space. Right, the next question is the reading on ammeters A3 and A4. We'll calculate this one later. Let's give it some time down here. Excuse me. So we'd like to find the reading on each ammeters A3 and A4. If you are not seeing where A3 is, that would be this one that we just finished. A3, we already know it's 1.5, isn't it? Because I did that method. But let's say we didn't know. How were we going to calculate A3? We were going to use the formula V is equal to I, R, and the current A3 is the current in resistor 16 ohms. So we'll be talking about V3 here. And the resistance we'll be talking about will be 16 ohm here. So I'm going to say V3, we just said it was 24 just now. And we want to figure out that current. So if we didn't know, we were going to do it this way. And then we're going to get that current by saying 24 over 16. I should think you are going to get 1.5 amp anyway. Okay, so you're going to do it this way normally. A4 again, it is this part here. Can you see A4 is measuring? It's this one over here. Hope you can see it right there. It's measuring the current in the 48 ohm resistor. Again, you are going to use V4 this time. And you're going to say IR. And in this situation, you'll be talking about 48 ohm. So V4, we also said it was 24. You wanted that R, and we're dealing with a 48 ohm resistor. So we were going to get that current anyway as 0.5. So you just need to be a person with a lot of ways of doing things, so you can use the one that works at a particular time. So that's the method we are using now. Well, let's go and calculate the power in the 3 ohm resistor. From what we have gathered in the previous lesson, there are 3 equations that we use, 3 formula we use for power. I said you may use your power as power is equal to current times voltage. So if you have the current through an appliance and the potential difference across it, you can use this formula. In this situation, I do have everything. Look at the 3 ohm resistor. I know that the current flowing there is 2. And the voltage across the 3 ohm resistor, we calculated it as 6. So I can easily calculate my power as 12 watts, for this one. But in this situation, I just really had everything. I had everything. So it means even this formula was going to work as well. Remember, we have 3 formula. So it's or, you can use this one. Your power, you could have said 2 squared for current multiplied by the resistance, which is 3. So 4 times 3 will still be 12 watts. And we don't want to forget that we could have used this one as well. So there are 3 formula for power. We want to get used to them. So depending on what we have at the point, we use this formula. Because at times you may realize that you have voltage only and you don't have the current. So you have to use this third one that we've got. So the potential difference there is 6. So 6 squared will be 36, and we're going to have to divide that one by 3. So definitely, you'll still get your power as 12 watts. So it didn't matter which method you felt like using here, you were going to get the power dissipated in the 3 ohm resistor anyway. All right, so some questions are not worth doing. Like question 7, it's asking what is the current, there is no need for time, the total current flowing in the ammeter A1 here. So if you look at A1, I'm just going to erase the green that's there. Look at where my eraser is. That's where A1 is. As you can see, A1 measures the total current. So the reading on A1 would just be the total current flowing in the circuit. That should be 2 amperes. It will be the same as the reading on A2 from what we have discussed. Right, now energy. Now this one is more interesting. When we talk about energy, I said just think of it as charge times voltage. But then from what we know, your charge is your current times time, right? Times voltage. So all you need to calculate work. If you had power, you could use, oh, actually you do. Is this in the 3 ohm resistor? Oh, sorry. Unfortunately, it's the 16 ohm resistor, so it's a different one. So you don't have power at the moment. You have current, however, flowing there. You know for how long, and you have the voltage. So let's go and do that. Do you still remember the current flowing in the 16 ohm resistor? Well, it's still there. It's the one that is being measured by A3, which we said was 1.5. Look at the circuit right there. It's still there. 1 minute. How long is 1 minute in seconds? That would be 60 seconds. And what is the voltage across the 16 ohm resistor? What was that V3? I think we agreed that it was 24. So as we can all see, this is the work done or the energy dissipated in the 16 ohm resistor in 1 minute. Use your calculator, please. Should get 2,160 joules. Not very bad. Okay, so that's our first question here with negligible internal resistance. So let's just have a few more, just so we can practice and get used to it. So here is our question 2. Let's see how well you will do this one. So look at it. We have a battery which has with a resistance which is negligibly small. So it means the EMF is 10 volts and the potential difference is still 10 volts. So even when the circuit is in use, so you want to keep that in mind about batteries that have what is it called? Negligible resistance. So small that we neglect it. All right, so we want the reading on ammeter, on the ammeter. So notice the ammeter is right here. So the ammeter will be measuring the total current flowing. So at this point right here, we seem to want the total current that's flowing. So it is the same current that will flow through the 140. That's our breakthrough right there. So we didn't have total resistance. So it was not going to be easy to use total voltage over total resistance when we don't have the resistance. But now we know that that same current is flowing in this one. So we can easily calculate it using our formula. V is equal to IR. Do you see that I have the voltage across the 140 ohm? So it is 2.8. I would like that current, which is actually total current. I'll put 140 here. So as you can see, my current can easily be calculated this way. It is so very small. Okay, so this is what I'm getting, I hope. 0.02. My 2 is now beginning to look like something else. So here is 0.02 amp. That is the current I am getting, which is flowing. So it is the one that passed through that ammeter right there. So if it is the one crossing the one passing through the 140, it means it's the total current right there. Let's not forget what I said to you in the previous lesson. I also said if you have voltmeters that are in series, so there is this voltmeter here, and then there could be another voltmeter I can put across this parallel combination, just right here. I can put it over there, so it can be a voltage on the parallel combination. If I add this voltage and that voltage, I have to just add it once. Please, I should be able to get the total voltage of 10. So why am I saying that? I am seeing this question here which say, calculate the voltage across the parallel connection. So do you see that I already have my 2.8 volts? So I would like to say VT here is equal to the V total is equal to the V that we calculated plus the voltage on the parallel combination. This one was given to be 10. And we were told this is 2.8, so we shouldn't fail to calculate the voltage in the parallel combination. I'm just putting those lines for parallel. So what is 10 minus 2.8? I hope it's something that you can still do. So that's 7.2 volts. So the reading here will be 7.2 volts. So what's interesting is that if I put a voltmeter here as well, it will read 7.2 volts as well. If I put it across this one, it will read 7.2 volts. So that's the beauty of parallel resistors. And of course, on the green one, you can see that it's the combination of the two. It will also read 7.2. Now, this one is rather interesting, the resistance of X. Calculating an unknown resistance can be easy, and at times it can be difficult. From where X is, we can see that it is part of the parallel combination. We would like to calculate that value. So if to make our lives easy, I may have to first of all know the total resistance for this part only. So for me to be able to know the total resistance for the parallel combination, I first of all have to know the total resistance of this circuit. How do I do that? I'm going to calculate the total resistance by just saying V total. You know that I can use V is equal to IR. Just cutting a few corners here. V over I. I have to use total everything. So the total voltage is that across the battery. What was it? It was 10. So that was 10. And what is the total current? The one that the ammeter is recording there is 0.02. From what I am gathering from all of this, I can see that the total resistance here, what is 10 divided by 0.02? So it should be 500, right? So the total resistance of this circuit, everything included, including the 140. If you include the 140 as well, you should get 500. So for the parallel combination, the total resistance should now be equal to 500, and then we take out that 140. So the resistance for the parallel combination now, we will see that it is equal to 360 ohms. We are almost close to what we should be doing. Okay, so after I get that, now I'm going to go and say, you know our formula. If we have 1 over R parallel, we can say is equal to 1 over R1 plus 1 over R2. You see, there are two of them, right? So I'm going to use this formula for you to our advantage this time around. R1 and R2. The thing is, I already know what the answer for R parallel is, so I'm going to put 360 here. I know that that's the solution. And then R1 happens to be the unknown. That's X. You still know that that's X, right? Okay, and then R2 is the one that is there, it's 600. So now we are just doing math. Calculate the value of x from here. So maybe the first thing you do is to subtract. Maybe you subtract 1 over 360, subtract 1 over 600. So I'm noticing that your 1 over x here, if you do that, you should get something like 1 over 900. Good. You should get 1 over 900. Use your calculator. And of course, if you invert this, your x is now going to be 900 ohm. So this one was not, it was an interesting sum to do to calculate that unknown resistance. So what did I do? I first of all calculated the total resistance of the circuit. I subtracted the resistance in series, this one, so I could be left with just the resistance for the parallel combination. Then I played around with it to get my x. As you can see, we have it over here. All right, now let's have the last one for this one, the last question. Okay, question 3 here. We have, again, the battery. It's actually more like a cell. It's more like a cell, the positive terminal. It has got to be a battery. 15 volts, no way. A cell, 15 volts? No ways. So we have a 15-volt battery, and V2 is the voltage across the battery, and R1 here, you can see that it is 3 ohm, so we want to keep that in mind. Here R1, and there is 2 ohm here, and we also have this 4 ohm over there. So these ones are parallel to each other, so we want to keep that in mind as we are doing this. So the first question is actually asking us to calculate the effective resistance of the circuit. So we would like to calculate everything. So we want to firstly calculate the resistance for the parallel combination. For me, let's do both. 2 times 4 product over 2 plus 4. So the R parallel in this situation, what is 8 over 6? That's 4 over 3. Okay, I'm getting 4 over 3. However, you, on the other hand, are saying 1 over R parallel. Maybe it's 1 over 2 plus 1. You may write the formula first. 1 over 4. So you should get, let's see, you should get 3 over 4 here. Okay, once you get 3 over 4, you invert that one and you get 4 over 3 ohm. Okay, normally this is the one that they like, so you go ahead and use that one. So that's for the parallel combination. So we have to add this resistor as well to this, so we can get the total resistance or the total effective resistance. So I have to say 3 plus the 4 over 3. So the total resistance for this particular circuit will be 13 over 3 ohm. So I'm going to write it as 4.33. In fact, because we may actually need 13 over 3, let me just write it here so I will remember it. Okay? 13 over 3 is that one to 2 decimal places. All right, good. So let's finish these questions. What else was asked? We would like to read or to calculate, if only we could read it out, the current reading on A1. So A1 is actually measuring the total current flowing in the circuit. So like I've already indicated, if you want total current, feel free to use total voltage and total resistance. We seem to have both of them. So total voltage is 15 and total resistance, did we just finish calculating it? You see, this is why I needed the exact one. What was the exact one? 13 over 3. I just really prefer we use exact things if we are carrying on something. Okay, so now this is not going to be a very good answer, but do use your calculator to multiply 15 by 3 and then divide that by 13. Well, I'm getting some 3.46. It was 45 over 13, so I'm going to write it as 3.46 amperes at that point. So that is the answer for A1. And just so we can have it safe somewhere, let me just write this answer. You see, this one was 45 over 13, whenever we want to use this current again. The rounded off figures are not always very convenient. Okay, good. So another thing we want to do now is to find the reading on V1. Okay, so the reading on V1, there are 2 to 3 ways of doing it. Here is the fastest way of finding the reading on V1. Just know that the reading on V1 is actually equal to the reading across both of them, like this, on the parallel combination. So if I can just calculate the voltage across this parallel combination like this, I can easily just calculate the reading on V1. So if I have that one, I can as well just say it's equal to V1 because they are in parallel. So how do we calculate the total voltage in the parallel combination? You use the total current in the parallel combination multiplied by the resistance, the total resistance of the parallel combination. So what I am saying is the total current flowing in this circuit, some of it will branch through the 2 ohm and some in the 4 ohm, but altogether it will come back to be 3.46. 3.46, it was actually 45/13, right? Multiplied by the total resistance of the parallel combination, which if you still remember, it's there, 4/3. So by calculating this one, it will be the same as V1. So use your calculator wisely here and see if you're going to get an answer. I am getting some 60/13 volts. I'm going to write that one as in 2 decimal places as 4.62 volts. Well, that's one way of doing it. What is another way of doing this one? Well, you could calculate, firstly, the voltage across the 3 ohm, that one. So if you can calculate the voltage across this one, then you know that the difference between that voltage, which let's call it V3. So V2 is going to be equal to V3 plus V1 from what we know. So let's calculate V3 first. To calculate V3, this is the voltage across the 3 ohm resistor. I may have to say IR. Where am I? Let me do this first. Not that one. This one. Good. That one. Put it here. Okay, good. So I'm saying, or this is a second method that I'm using here. I'm calculating the voltage across the 3 ohm resistor, and that would be, what was our current, the exact one? 3.46, but it was 45/13. And the resistance in question is 3, right? So the voltage across the 3 ohm resistor, which I'm calling V3 right now, is actually going to be 10.38. Okay? But from what I said, if you remember, I said the total voltage, which in this situation is V2, should be equal to this voltage over here across the parallel combination, or across the 4 ohm, which is V1. So it should be equal to V1 plus V3. Look at it closely. So our V2 in this situation is 15, and our V1 happens to be what we want, and then V3, we just finished calculating it here. So that's 10.38. So if you don't mind, we will subtract those two, and we will be surprised to get the same 4.62 volts. So it should be easily calculated like that. So you can do it that way as well. So no limit to what you can do. You can as well make the current branch. You know, you can really. You know, when the current gets here, it branches. Some of it goes that way, and some of it will go this way. So you can use the ratio. You can see that the ratio is here of the resistors is 1:2. So that of the current will be 2:1. So you can branch the current like that. So let's go and see the next question, which is our last one for this one. So let me put this one a little bit this side. So we want to calculate the reading on ammeter A2. We had that one coming for a while, isn't it? So we have again two methods of calculating the reading on A2. As you can see, it is measuring the current flowing in the 2 ohm resistor. So I am saying if this voltage here is 4.62, we just finished calculating this to be 4.62, right? So even the voltage up here will be 4.62, the voltage across this one. So that's what you can use. You can use the fact that we have that voltage because they are in parallel, right? So you use that 4.62. You see, now we are going to use something that wasn't exact, but I didn't have the exact one for it. So our current is what we are trying to find. And the resistance in question is 2. So your current that you should get in this situation should be 2.31 amperes. So you can do it that way. And if you still remember, I said you may use your ratio. Do you see your ratio is still here? 2:1. So you divide your current into 3 parts. You know that 2 of the 3 parts of your total current, what was your total current flowing in this circuit? Let's find it. Not there. Did we calculate it somewhere? Yes, we said it was 45/13, right? So 2/3 multiplied by 45/13, that was the exact current that was flowing, should be the current flowing in A2. So if you do it this way as well, notice you will also still get your 2.31 amperes. So this way, people, is the way to do electric circuits. From the next lesson onwards, you'll see how I will treat internal resistance and use it exactly in the same way. So let's wait for that one. But for now, thank you very much for watching this video right here.